Let's find the arc length of the curve defined by r of t equals cosine of t comma sine of t for t starting at 0 and ending at 2 pi. So if we set up this integral, there's just the formula copied, and we will just write it in this other format. So we've plugged in the 0 and 2 pi for alpha and beta. The other format of I mean, we could do it more direct, but just the other format of this was the magnitude of the velocity vector function. And let's see, I just copied the magnitude notation just to compute the velocity vector itself. Cosine of t differentiates to negative sine of t, and sine of t differentiates to cosine of t. And now we have this vector function to take this new vector function, right? This is our prime that we need to take the magnitude of. So that will so here's what the integrand becomes. We have a radical negative sine of t quantity squared plus cosine of t quantity squared. Of course, squaring is going to get rid of the negative sign anyway. So inside the radical, you actually have sine squared t plus cosine squared t, which you know from the most famous trig identity is just going to be 1. So we have root 1, which is of course just 1. And if you integrate 1 from 0 to 2 pi, you get 2 pi. I hope that makes sense. Think of what the curve is, right? Does 2 pi make sense as the arc length? Does this formula, even though we didn't prove that this should be the formula, does this seem to make sense? Is it giving you the answer you expect based on what the curve is? So stare up at the vector functions formula up here at the very top and think about, does that seem right? 2 pi as the arc length? Okay, let's parameterize the line segment from the point 3,5 to 711 and then find the arc length of this curve. So here is the parametric form, x equals 3 plus 4t, and y equals 5 plus 6t. Just spot check, does that work? When you plug in t equals 0, I hope you get 3 comma 5. And when you plug in t equals 1, yeah, x is 3 plus 4 and y is 5 plus 6. Yeah, that seems to work. Okay, so as a vector function, this is 3 plus 4t, comma 5 plus 6t. All we're doing is taking the x and y formulas and just organizing them as the components of a new vector, well, of a vector function. So it's just the same information, just organized technically in a different object. Okay, let's apply the formula. So we're going to go from 0 to 1 because t starts at 0 and ends at 1. If you take the derivative of 3 plus 4t and 5 plus 6t, well, the derivative of the constants 3 and 5 becomes 0, right? Those derivatives are 0. So 4t differentiates to 4, 6t differentiates to 6. And now if you'll take a look, we need the magnitude of the 4, 6 vector. This one doesn't even have any t's in it, right? But let's just compute the magnitude the way you'd expect, right? Root 4 squared plus 6 squared. And then here, if you integrate a constant from 0 to 1, you just really literally get the constant back. You can do all the work if you'd really like. But does that make sense? So here's the interactive question. How could you have gotten the same final answer without doing any calculus at all? Think of what object you have up here and explain your process as you would to an algebra student. Now this may seem strange, but just keep in mind that the object is not like the last one, which was a circle. Just think of specifically the object we have, and is there a way for a student who's in college algebra to compute? Of course, you probably are not going to bring up the word parametrize, for instance, or say arc length, curve. These are probably words you're not going to use, but is there a process that ought to be familiar to an algebra student that should result in the same number?